The video.
Filtering of noise corrupted signal using moving average filter. बताए कुछ समझा नहीं, आगे नाटो बता दे.
Okay, so what we are basically doing over here is ये हमारा input signal है. Okay, you can see my camera. ये हमारा input signal है. This looks better, ठीक है. ये हमारा input signal है, and we are corrupting it with some noise. So we have got this noise corrupted signal. You can see the ripples. Now what moving average filter does is it smoothens out the curve of the signal. Basically क्या कर रहे हैं, जैसे example if we are taking the 40th sample over here, तो 40th sample का अगर 3 है window size, तो 40th sample के पहले वाला sample and 40th sample के next वाला sample, तीनों samples का values add होगा divided by 3, मतलब basically तीनों samples का average लेंगे and यहाँ पे वो value डालेंगे. So basically what this does is this smoothens out the curve, and that is filtering the noise corrupted signal using moving average filter. So we start with the program, going to new script, and this is the program over here. The first three steps are again the same: CLC, clear all, close all. R equals 64. That is the length. That is the number of samples that we are going to have in our signal. That is 64. Now D equals RAND. 1 comma R minus 0.5. RAND is nothing but a MATLAB function that generates random values between 0 and 1 for noise. That is basically used for generating noise. So what we are doing over here is RAND 1 comma R will give you a matrix of 1 row and 64 columns, each having values between 0 and 1. Now since we wanted the signal to move above the actual values and below the actual values, what we are doing is we are going to subtract this values in this RAND matrix by 0.5. So we will get values between minus 0.5 and plus 0.5 instead of 0 and 1. So next is just remember this step. We don't do it for any other programs. We have to write S of m and X of m over here. For m equals 1:1:64, that is 64 values with the step size of 1. Sm, that is the input signal, is given in the question, that is 2 into m minus 1 into 0.9 per m minus 1. Xm is the noise corrupted signal, that is Sm plus D of m, where D is this function. And we end the for bracket. Now we'll first plot the input signal and the noise corrupted signal. So subplot 3, 1, 1, m equals 1:1:R, plot m, Sm. Similarly for m, Xm. Now we are going to generate the moving average filter. So we'll ask the user to input the length of that moving average filter. So m equals input, enter length of moving average filter, MAF. Now what this H does is, H will give you the coefficients of the moving average filter. So for a moving average filter of length say 5, we will have 5 coefficients, with each coefficient being 1 by 5. For a moving average filter of length 3, we'll have 3 coefficients with the values of each coefficient being 1 by 3. So H is 1 comma m, that is we'll get a matrix of 1 row and m number of columns, each having values 1, and then we divide all those values by m, so we get the coefficients for the filter. Now we are going to convolute H and X. So we are basically passing the input signal through this moving average filter, and we get y equals CONV H comma X. Now for the length of y we do the same thing, L equals length of H plus length of X minus 1. So for Z equals 1:1:L, subplot 3, 1, 3, plot Z comma Y, that is the smoothened out filter. We click run and advance. We click on the run and advance command. This is the input signal, and this is the noise corrupted signal. You can see the evident ripples over here. Now we are asked to enter the length of moving average filter. For example, we press 7. We enter 7, sorry. And then we get the smoothened out curve of the input signal. So basically the signal has been filtered using the moving average filter, and we partially recover the original signal.
Thank you for watching.